Welcome to this presentation, which covers the enhanced graphing capability of the Si9000e. The optional projects facility in Si9000 has been enhanced so you can automatically graph the output of a range of project structures. You can also create projects automatically from a sensitivity analysis, which makes rapid analysis of insertion loss variation very straightforward with Si9000e. I'll also look into goal seeking of copper roughness and correlating measurement with modelled information of insertion loss, and finally add in a few details on the improvements to the trace resistance calculator, which now covers temperature gradient and temperature coefficient. It does require the SI projects feature, and that'll be used throughout this presentation. Here's an Si9000 where we're using the projects feature, which is an ability to save each structure with its dimensions and have a structure for a particular project with a number of other structures alongside it. And you can see here, if you right click in this area, we've got a new graphing tool appearing in this dialog. What I've done is put in a range of identical structures from a geometrical perspective and a coating perspective, but the loss tangent is different on every one. So it's a nice simple introduction to this facility. So when you right click in the project list, you'll see this new graphing tool. And when we operate that, we then get into the graphing dialog, which shows you the structure list, whether you want to graph the particular structure or not. So you can select from the list which you'd like to graph. There may be some on different layers that you don't want to compare, so it's easy to include or exclude structures here. And then here you get all of the dimensions for the particular structure that you've selected. When you run this, you then get a graph showing the plots for each structure in the list. So in contrast with the Si9000 as it used to be, you could only do one graph for any one structure at a time. This allows you to overlay and change any particular parameter within the structure and contrast the results that you get from that modelling. In this case, you can clearly see the impact of loss tangent on the total attenuation. So here's another example, and instead of loss tangent, in this case, we're going to alter the roughness. So from 0.5 micron, 1 micron, 1.5, 2, and 2.5 microns. So I've generated a project with all these different roughnesses. And here you can see the loss versus roughness for otherwise identical geometries, and the band from an almost smooth to a 2.5 micron roughness surface, and just how significantly that changes the loss from around about minus 8.9 dBs per inch right down to here to minus 2 dBs per line length. So it's a very powerful feature for comparing changes of one or multiple parameters within structures. Here's another example where I've actually done a lot of data points, and in this situation what I've done is to model 100 ohm structures, and the width and separation have been set to maintain the impedance. So we've got a number of structures all on the same stack up where I've made the trace width narrower and then closed the separation off to hold a constant impedance, and shown how all of those 100 ohm differential pairs will have different insertion loss based on the degree of coupling. So in summary, that new graphing option provides a what if capability, and it's limited only by your imagination. You can imagine any scenario and rapidly graph the output. But you do have to make the project in the first place, and so we've added some tools to make that a lot quicker. If you run a sensitivity analysis, and you might be familiar with this from the impedance side of the Si9000, Si9000, you can sweep a range of heights or a range of trace widths and generate a sensitivity analysis and graph that. So we've taken that on to the next level, and with the projects feature, you can take a sensitivity analysis and automatically create a project. So in this example, we've taken a constant impedance line here. We've swept the height from 3 to 12 mils, and the trace width has been calculated to have a constant impedance of 50 ohms regardless of the height. So along the bottom of the graph here, we've got the height from 3 to 12 mils, and then the line width. As the height increases, as you'd expect, you increase the trace width, and every point along this line represents a 50 ohm transmission line. So if we'd like to do a bit more analysis on this, at the moment you'd have to take each individual point and make a project and then graph the parameters for each particular step along the line. But it's a lot easier with the latest version of Si9000. You simply go into the results tab here and flip into that. So the results tab is here. Here's the height and the width and the impedance, in each case 50 ohms for each particular height and line width combination. So making sure you flip from graph to tabular results, and then if you right click in the results pane, you'll then get a create project structures dialog, and by clicking on create project structures, if you come and look over here, then create project structures, that's taken every height increment and created a structure for the project for each increment of height. So very rapidly, in just a few mouse clicks, you've gone from a scenario where you've got one structure to a group of structures from 3 to 10 mils, and now you've got a project, and now you can then move on to use the graphing and graph this. So let's step through the steps to do that. It's also worth noting that the structures are auto named and dimensions. Forward into the next slide. In a couple of clicks, you create a graph like this, which has taken all of those structures by right-clicking the graph control, and now you've got a graph which shows you height, width, constant 50 ohms, and how over 10 different steps you've got 10 different levels of insertion loss. Once you've created the project, then you might want to come back to it in future, so you can file save as SI project format, and that can be shared with other Si9000 users and pulled back for later use. So it's a very, very powerful graphing tool within the Si9000, which extends the capability from the single graph capability of earlier versions to allow you to rapidly generate multiple graphs of insertion loss or other parameters that you may want to graph. We've also added a new feature which many customers requested, and that's to be able to goal seek the copper roughness to match measured results. So you might be pulling in the measured results from a VNA. You could be using the Polar Atlas. You could be using another VNA with some Delta L processing software. And this new capability allows you to goal seek the copper roughness when you're trying to correlate measured and modeled results. So in this slide, we've brought in a differential pair transmission line, and we've modeled the smooth conductor loss, the dielectric loss, the smooth attenuation, the conductor loss with attenuation, and the conductor loss attenuation with roughness, which is the total attenuation for the trace. And in this case, the correlation is pretty good because we've brought in the measured results from the vector network analyzer, and you can see that there's a pretty good correlation all the way up to 40 gigahertz. But that may not always be the case, and you might want to see if it's roughness that's causing that miscorrelation. So with surface roughness, you can go in and goal seek now, and to do this, you would enter the total attenuation at a given frequency from the insertion loss measurement, followed by calculating the dielectric loss for the frequency entered from the structure. And then when you subtract this from the calculated dielectric loss from the total attenuation, it leaves the target conductor loss. Then you use the Goalseek algorithm, and that varies the surface roughness until it matches the required value. And in this case, it predicts the surface roughness is 2.27 microns. Again, it's very important that you take that data and go back and verify against the microsection to see if you've got it in the right order. So that's really important that you don't just assume it's something. It's important to go back and look at the real data from the section material. Also worth noting here, we're using Cannonball Huré, which for low levels of roughness and for high frequencies is probably the best roughness method to use. The goal seeking will work on the other methods within the Si9000, but those models such as Hammerstedt and Greuss, they only go up to sort of 4 or maybe 8 gigahertz, whereas the Cannonball Huré and the Huré method is a much higher frequency method for lossless modeling. We started off with quite good correlation anyway, but in this situation, you can see here, where now we've done the goal seeking, we've really got a very good line all the way with a fit all the way up through to 40 gigahertz. So that's the surface roughness goal seeking option in the Si9000. Just to note again there, the cyan is the model attenuation with roughness, the total insertion loss, and the brown is the insertion loss measurement data, in this case taken from a polar atlas. But always remember, always use microsections, always test your assumptions. Did you actually make what you thought you made? Because it could be that the reason for the insertion loss difference is actually maybe a wrong material was used and the tan delta is different. Maybe the copper was narrower than you thought it was, so it's actually a copper dimension rather than a copper roughness. It's important that you're aware of the underlying physics of your structure before you take an assumption that it's just the roughness that's causing the correlation difference between measured and modelled. And finally, we've made another small addition. Because sometimes electronics were on hot, we've added temperature coefficient added to the trace resistance calculator, which is an add-on. So here's the new trace resistance calculator. It's got an all-new look, and we've allowed it. We had some customers request longer line length values and to add the temperature coefficient of resistance. So we've added both those capabilities into the TRC. So it lets you add a conductivity and the coefficient of resistivity, conductivity per degree C. We've made the whole TRC interactive image. So you can select a material via the drop-down list. You can click on any particular parameter and then enter the data for it. Switch to your preferred units by clicking the associated dimension button for mils, inches, microns or millimeters. You can enter or change the track dimensions and it will live update the results. It auto updates the trace resistance and the voltage drop will be displayed for a given current in the voltage drop box. So it's a very simple add-on, but it's quite useful, quite powerful add-on to have a track resistance calculator where you can also simulate the effects of temperature on your PCB trace. A couple of other small things we've added to the Si9000 and the Si8000. We've now added an option to export the iterations of Monte Carlo analysis to the clipboard for Excel. You can right-click that out of the Monte Carlo analysis. And we've done the same for causally extrapolated substrate data. So when you're doing causal extrapolation on the dielectric constant and tan delta, you can export the results to clipboard so you can access that in other programs. I also add that with our other tools, with SpeedStack, we've got a huge library of material data which we regularly update from all of the material suppliers. So if you need access to updated material supply data, it's readily available within SpeedStack, and if you've got SpeedStack, you can paste that through into Si9000. Thanks for watching this presentation on the latest features in the Si9000, which include graphing, creating sensitivity analysis from projects, and enhancements to the trace resistance calculator. For more information, please do contact your local Polar office.